Okay, so we talked about homotopies and homotopy equivalence, and then we gave all those conditions, and we gave a bunch of examples, and all of our examples have been about a certain type of homotopy that I want to talk about, and that is a deformation retracts. Okay, so these are the things that give rise to homotopy equivalences. Okay, so this is this idea that you'll have you'll have a disk right here, and then you can actually you can retract it to a point, right? Okay, and but this is actually a deformation retract because so this is a retract here. This is a retract because so this is so we have a map R from X to A, where this is X and this is A, which is the point, and this is a subset of X. Okay, so we can kind of view this as a map from X to X, right? And this satisfies. Oh, actually, let's do it like this. It's a map from X to X. So sometimes I'll call this to X. Sometimes I'll call it to A. Okay, so it's a retract, and it satisfies since. Okay, so this is a retract since one R restricted to A is the identity on A. It's identity on this point, and so this is the map here for just to be completely concrete. So this is D2. This is the point 0. And then R of XY, this is just 0, or 0, 0, right? Okay, so that's to be completely concrete about that. Okay, so it has to be this, and then we also need that R of X is equal to A. If I phrase it like this, so this is what a retract was. Okay, so what's a deformation retract, right? So a deformation retract is one that deforms. So what's a deformation retract is, so like let's do this thing. So what we can do is we can continuously deform it here. Right, so if we go into our example like this. Okay, so here I can look at this map, f of, so I'm doing xy, so xy t, I guess I'm doing t in the second component. And I could just write 1 minus t of xy. Okay, 1 minus t times xy. Okay, so this is a scalar, this is a vector, right? And then as t gets bigger, it shrinks and shrinks. So what we've done is we've kind of taken this map. So we have a bunch of maps, okay? And so you'll note that f of 1 is R, okay? And f of 0 is the identity. Okay, so a deformation retract in general so what's a deformation retract? It's a retract R from X to A, or so let's say X to X. Okay, we'll write it like this: A subset of X. And so we're going to view this as a map from X to X, such that R is this is homotopy. So I guess maybe so I don't. What do I want the homotopy, or do I want the map to be the deformation retract? I guess you could do it either way. So let's call so a retract is deformation. So do we want deformation retracts to be retracts, or do we want them to be deformations? I may regret this. Let's do. Let's abusively call them both a deformation retract. Okay. So is a retract such as this? So abusively. we will also call F the deformation retract. So let's just make this remark, because I will do that. Okay, so we have a retract that is homotopic to the identity, and so it is so let's make another remark in that so we say F is strong. See, I already did it. If and only if. So it's a strong deformation retract if and only if Ft restricted to A is the identity on A for all T in the interval. Okay, so this is a strong deformation retract. This one is strong here. So this is an example of a strong example. Okay, so that's another example. So you could remove. So another thing is you can remove. So let's see. Yeah, I mean there's lots of examples. We've already talked a lot of examples. And so what's the point of deformation retracts is that these are all. So a good exercise. Right. If you have a deformation retract, then it induces a homotopy equivalence. Retracts give homotopy equivalences. Okay, and so what do I mean by that? I mean that if i.e. if f of t, let's say if r, okay, now I'm going to call the retract the map. If this thing here, if this is a deformation retract. Okay, now then x is homotopy equivalent to A. Okay, so for example, right, the disk is homotopy equivalent to a point. Okay, and all those other things that we showed were homotopy equivalent. Linked. R3 minus a circle and a sphere wedge a circle. Right. That's an example of two things, that a deformation retract, and so that they're homotopy equivalent. So that's the point, is that if you can do those deformation tricks, then you get these homotopy equivalences, and that's kind of like our means of producing homotopy equivalences. And I haven't given any example about things that are not homotopy equivalences. So what is an example of? Okay, so let me kind of make an important remark. Important remark. Right. So pretty much all homotopy equivalences come from deformation retracts. All equivalences, all homotopy equivalences come from deformation retracts. Okay, so cool. So what do I want to say now? So what do I mean by, okay, okay, I need to say a little bit more about that. So the theorem is the following. Okay, is that if if x is homotopy equivalent to y, then there exists some z z and two inclusions, right? So this would be the inclusion. Where Z so is so where Z deformation retracts to both of them. Okay. Okay. So okay. So we showed things that where you could collapse things. So okay. So this is like okay. So now we're getting into some really interesting things. So how does this work, right? So how do we do this? Okay, and so the key ingredients here are this thing called the homotopy extension property. All right, and these other things called co-fibrations. Right, and then the other thing is the mapping cylinder. Okay, so let me say a little bit about this. Okay, so let me give you an example of a deformation retract. So let's give an example of a deformation retract. So here's kind of an important example. I've already done this. I don't know if have I done this one. Okay, so we're going to take a map of topological spaces like so. Okay, then we have this thing here. Okay, so now I'm going to draw this thing. Let's draw it like this. Okay, so here's X. And we're going to have a bunch of copies of X down here. And then here's Y. Right? And then here is maybe f of X inside of Y. Right? And then we're going to kind of draw a cylinder here. Okay? So we've kind of glued this cylinder onto X. Right? So this thing is this is the mapping cylinder. Okay, and this is this thing MF. This is an incredibly important example because it really is like the main example of things. So let me show you this retract. So let's give the definition though. So this thing here is so what do we do? So we took X cross an interval, right? X cross an interval. So that's like this, right? And then what we'll do is, and then we'll take Y here. Okay, so we took Y. So this is X cross the interval. This is Y. And then what I'm going to do is I'm going to impose an equivalence relation on this, where down at the bottom half, so this part here is X cross 1. So here's 0 and here's 1. Okay? So this is the top of the interval. This is the bottom of the interval, and then I'm gonna make identify the points on here with their image here, f of x. Okay, so we've kind of taken this cylinder, and then we've glued the bottom of the cylinder onto this space y, like so. Okay, so this is the definition of the mapping cylinder. Okay, and what I want to say about this is that so what the important property is. So this is kind of a cartoon of the construction Okay, and the important property, the important part of this is that the mapping cylinder is homotopy equivalent to. So this thing here is homotopy equivalent to y. Okay, so this is what I want to show you. Okay, okay, this is one of the properties. Okay, so how do we do this? So so what we're going to do is we're going to do a deformation retract. Okay, and what we'll do is we kind of just sloop this thing down. Right, so we'll take this guy, right, it's in Y like this, and we just kind of move it down. So that's the retract. So this thing just, you kind of push it down like so. And we don't know that this contracts onto here, so but we do have this thing contracts, right? So this is the deformation retract, and this deformation retract implies the homotopy equivalence. You get gives homotopy equivalence. Okay, and then you can. I think a good exercise would be to try and write this out in coordinates. Okay, and so by coordinates I mean you just use x's, t's, and y's. Okay. Okay, so that's the deformation retract. Okay, so what's an example of something where you can't? So like there's another construction that's similar, and so I just want to mention there's another thing where you can't do this. So there's kind of a variant. Right, and this is the mapping cone. Right, this is CF. Okay, and so for the mapping cone, right, we do the exact same thing. Right, so this is f of x. It's sitting in y. Right, and all we've done is we've kind of collapsed. So here's MF, here's CF, and there's a map like this, which takes this thing here, right, and this collapses it to a point, right? So it's a collapse. And we know how to collapse. We just mod out by, we take a quotient. Okay? Yeah, and so here's here's the copy of y, and then here. But you notice that in each of these things, right? So like here, if this is the slice x cross t, right? And this little piece here, this is isomorphic to x. Right? But now since you've crushed this point, right? You can't really like slide it down. Right? You can't slide this whole thing down to these pieces. So now it doesn't slide anymore. Okay, so the last thing that I didn't want to say, but maybe okay, I'll say it. It doesn't hurt to repeat it twice. So one of the things that I want to say is a property of the mapping cylinder. Okay, is that so if you have so you can take x, right? I can stick it into this thing MF, right? And then I can project this thing down into y by so this is the retract, right? And so there's this thing. So this is okay. And what is this thing? So if I do this whole thing, so this is include at the top. So this is include as a slice, right? So here is this thing, and now I include it into the top here, right? And then I project this thing down. So I just go back down like this. Okay. So maybe I can call this I0. Okay. So we include here. So this goes into this slice here, right? And then this thing, smooshes it down. This part here, from here to here, this is a homotopy equivalence. Okay, let me also say what this is. So this map here, if I were to go all the way around like this, right? What is that map? If I were just going to do here and then go down. So that's the map F. So if I'm given, F from X to Y, it factors as this map here followed by this map. So every map can be factored in this way. Okay? Yeah. So this is the homotopy equivalence. So this map here, R, is a homotopy equivalence. It's a deformation retract. And then this map here is this very special property. So this thing here, yeah, so this map here is what's called a co-fibration. This is what's called a co-fibration. Okay, so this is one of our building blocks. Okay, and then we'll talk about this. But the point is that this thing has what's called the homotopy extension property. So let me say, maybe I can say a little bit, yeah, so how much do I want to say about this? Let me pause and think about it for a second.